So the next thing I'm going to talk about is the paper by Kruse and Strack. And the main result in their paper is first they assume that there's only one possible action after they stop. So it's basically there's only one thing they need to implement, it's the stopping rule. There's no terminal action to implement. So the main result of that paper is stated in terms of something called the marginal incentives, which is the Z function, which is expected to in the next period, not in all future period, but in the next one period subtracted by the current utility. And in the paper, they call it the single crossing condition, which if this Z function is now increasing or decreasing, then a stopping rule is implementable if and only if it's a single cutoff rule. They call it cutoff rule because they don't have binary cutoff rule. And also something great that they found is a closed form expression. So the prices are not recursive. They have a closed form expression for it. So what I'm going to do is I'm going to extend that to multiple queues. So we have a queue within some interval. In my paper, it's possible to have not continuous ones, but then this derivative condition needs to be changed. In any case, suppose it's continuous in some interval, then we suppose this cross derivative conditions satisfy. Then the two important conditions that we need, sufficient and necessary condition for implementability of all single cutoff, all the single cutoff rules are these two. So the first one is the Spence-Merlis condition, which is the familiar one that says Q is increasing. The second one is the single crossing condition. Also, it's directly from the paper by Pavan, Siegel, and Toika, which is the general dynamic mechanism design paper. And from their paper, they have a very complicated single crossing condition. This is a very simplified version of that. And this basically says, so suppose we say there's only one action, then what this says is the slope of the utility in the current period is larger than the slope multiplied by something, and take an expectation conditional on this period's evaluation. And that something is the impulse response function. And from the Pavan, Siegel, and Toika paper, the impulse response function, basically quoting them, they captures the marginal effects of the current type on the future ones. And now the main theorem. So under the previous assumptions, Q satisfy those two conditions I just talked about, Spence-Merlis and single crossing, if and only if this decision rule is implementable for all single cutoff rules. So for any single cutoff rule, this thing is implementable. And the converse is not that strong because it says if all of the single cutoff rules are implementable, then those two conditions are satisfied. It's not if one of them is implementable, then those two must be satisfied. So it's not that strong, but it's an even only if statement. So before I give the proof, which I will, not the complete proof, but partial proof, I will just give you an example why these two things need to be satisfied. So I will go back to the investment example where the agent collects information about a project, and then the agent decides how much to invest. And two more assumptions that I will make is first the form of the utility function, which is the discounted quantity, not the quantity, discounted investment multiplied by the valuation subtracted by some cost each time for collecting that information. And the other assumption on the stochastic process is additive random walk, maybe with different GT at each time. So the first two lines repeating the assumptions, and then the Spence-Merlis is the same, but the single crossing condition becomes very easy to explain. Basically, it says the investment tomorrow must be, the investment today must be larger than in expectation discounted investment of tomorrow. And also a modified version of the closed form formula still applies, but I didn't write it here because it's very long. In any case, we should take a look why that single crossing condition must hold. So I will give one example. Suppose there are only two periods, the discount is 1, and the G function, the additive part The random additive part has mean 0, which makes it kind of a martingale. And suppose we want to implement in the first period, we want to implement x. In the second period, we want to implement something larger. So remember, the single crossing condition says the current period must be larger than the discounted future period. So this one is not right. So then we calculate the stopping value and the continuation value. Then we draw them out. Then we see that they have this relationship. Then you can probably see from this diagram this is not good, because on the right we have continuation value being larger. So we continue on the right and then not stop on the left. So this is not the single cutoff rule is. This is the reverse of the single cutoff rule. So if you imagine if it's part increasing, then some part of them will be like this, the other one will be reversed. So then it's not even the single crossing, the single cutoff rule, other direction. That was confusing. But anyways, let me give you something that actually works. So if it's today is x, the next period is half x, then it's smaller. By the way, smaller because that x, that stochastic process is kind of martingale. So it's when you discount it, it's the same thing. It's just x versus half x. So you have x always larger than half x if it's larger than 0. And this does satisfy the single crossing condition, and we compute these two things again, and then we see this structure, which is right. And how we want to implement anything, we just move it around, right? So we just change the price at time 0. So if you go back, we just change this P0, P0, B0, then we just move this around, and then it can be, we are implementing everything. So now moving on to the proofs. So the first step is very easy. So it's just the standard static mechanism design problem where the Spence-Merlis implies Q being implementable. And the second part requires some algebra. So the single crossing implies Z being increasing. So I'll show you the algebra here. The marginal incentive is basically, I'm restating that marginal incentive. And after some integration by parts, we will get this derivative being exactly the same as the difference of these two. So where the single crossing condition is just says this one part is larger than the other part. So we know that this derivative is smaller or equal to 0 if and only if that condition holds. Then we show that basically they are equivalent. So the single crossing condition is just equivalent to the marginal incentives being increasing or decreasing, whatever that is. So then after that, we have Kruse and Strack. Right, so Kruse and Strack did not go through these two steps actually, but their proof can be converted into something like this. So basically we have said monotonicity would imply the UV difference has the monotonicity condition, have the monotonicity property, and then which implies tau being implementable. So basically, to look at this diagram as a whole, the only thing I did is some algebra here, which is not really that much. So I have the converse here. In Kruse and Strack, they didn't prove the converse, so I did it. So going back, implementable implies Spence-Merlis is the same, and the next one requires some intuition, not that much. So if you look at this diagram, if at any point this U and V are not monotonic, so if it's decreasing at some part, then we see that at that point we won't be able to implement a cutoff rule. Because if we want to do this, we make them intersect. And then the problem is it works locally, but when it gets back to the normal increasing, decreasing part, it goes back to like on both sides, U is above V. So on both of the two sides, we have stopping. In the middle, we have continue. So it's not a single stopping rule. So this does not work. So that's basically intuition how I prove this. Anywhere it's decreasing, I show that it's not possible to implement at that point the single cutoff rule. So going back to this diagram, we need some more algebra to do this. So the basic idea is we can write V as a sum of all sets, and then we do induction to show each one of them must be increasing because the whole thing is increasing. And then the last one, as I showed you before, is the same because it's if and only relation. They are basically the same thing.